Hello again, it's me, it's Clara, and I'm here talking about more science. And in this episode, we're going to be talking about another thin film deposition technique called Pulsed Laser Deposition, PLD. So this is another physical vapor deposition technique which we use in the lab, and I actually use this in the lab. So we have a couple of chambers in our system, so I can actually show you what they look like. I took some pictures back when we were allowed to go in the lab, of course, because before all the craziness of the current pandemic lockdown. And so yeah, let's see what I use and let's talk about it. Alright, so I said that I'm going to be talking about pulsed laser deposition, so boom, there we have it, title slide, sorted. And yeah, so this is another physical vapor deposition technique. So, and I mentioned in the last video that a lot of these deposition techniques have, you know, certain characteristics which are similar to each other. And that's true. So once again, we have a chamber. We have a metal chamber. And again, it can be any shape, any size. In this case, I actually have a picture of my lab with two chambers set up. So this is one of them and this is the other one. It's hard to see because everything in my lab is washed out white and it's all grey and silver. So it's not necessarily the clearest to see, but we have this metal box with all these different windows and ports on them, and we can use them for different things. Here we can insert different gases. We have various pumps that I talked about, and we have motors to move things around. In the background, we've got this large fish tank looking thing, and I'll go into that a little bit more on another slide. So again, we have the chamber, and again we have the substrate. We have the substrate in there, and we have our target material. So this time, if you remember with evaporation, we had a crucible or a ceramic boat, and we melted our target material with that, our depositing material with that. In this technique, we actually have a thing called a target. And so this is basically a chunk of metal made of the building blocks that we want to use. And so it can be a metal, it can be, say, I keep on saying titanium as an example. So it can be titanium, but it can also be some sort of alloy. So we could have titanium nickel, it could be an oxide, so we could have titanium oxide, and we can have various compositions. So we can have various lithium compounds, because we do a lot of battery deposition in our lab for lithium batteries. So we can have a material which is lithium based, and we actually have a chunk of this material. And once again, it's a case of we start with the basic elements that we want, the basic materials we want, but it's how we change the structure when it lands on the substrate that's really important. And in the last one, what we did was we heated up the substrate until it evaporated, and that's how the material traveled through the system. Once again, we're doing this under vacuum, so there's no air, so that can't interfere. It can't knock our deposited material, our deposited flux out of the way. And also we don't have materials in there that we don't want, such as oxygen that might cause an oxide if we don't want an oxide, or nitrogen if we don't want a nitride. So again, it's very similar to what we saw before, but this time we have this. So we have a class 4 pulsed laser. It's an invisible laser. So there's 4 classes of lasers, 4 main classes. Class 1, which is kind of your basic low level lasers. Class 2 gets a little bit more dangerous. Class 3 is like, oh no, you've got to take quite a lot of precautions with them. And class 4 is basically the highest power. Even worse if it's pulsed, ours is pulsed. Even worse if it's invisible, ours is invisible. It's actually got a wavelength of 248 nanometers, so that's in the ultraviolet range. So if we turn all the lights out, we can actually see this very slight ultraviolet glow as the pulse travels around the I mentioned before the fish tank. I'll show you that in a second. But what we do is we take this big laser and we fire it into the system. So hopefully, boom, there we go. So obviously it doesn't look like extended lightning, but we do fire the laser in. It's very, very focused so that it hits a specific point on the target. And this, basically, it's a flash evaporation. It knocks off the atoms. They flash evaporate, travel through the vacuum and land on the substrate. Now, we can move it in various ways, but what we're doing at the moment, what we do with our system is we then move the substrate and we move the target. However, with other systems, you can actually move the positioning of the laser, which is quite a tricky thing to do. So I just want to talk about the laser. So so the substrate and the target move. Like I say, there are different ways of doing this, but this is how we do it. Now I said that we've got this fish tank. So basically what happens is that in order to make the laser more intense, we take this high power laser and then we bounce it off a whole bunch of mirrors. So in our system, it comes up from the bottom and it bounces off a mirror and travels through. This is an attenuator so that we can just change the angle a little bit, and it travels along through this big massive space where it bounces off another mirror, and then it bounces off another mirror, and then it heads back up the run, and it bounces off another mirror, and then it bounces off more mirrors, until eventually we focus it. So we actually bounce it down through a magnifying lens, and this focuses, so we've got a very, very, very fine point, and it enters our chamber. So this isn't under vacuum, this is in air, although it is people are protected from it, obviously. And then it's focused through this magnifying glass, travels through the it travels through there's a glass window in the chamber, and it's focused so that when it hits the target, the surface of the target, it's a very, very small defined area. We know exactly what size it is, and so by doing this, we've got very high, very intense energy with this laser. And so that's what we do, which is why we knock off atoms at a time, or we flash evaporate atoms at a time. And so yes, we hit it and then we move the target and the substrate. Like I say, you can move the laser so that it hits a different area of the target, and ours is capable of doing that. But in our case, we keep it focused where we want it, so that the laser's always hitting the same spot within the parameters of the chamber, and the target moves around. And also because then we're hitting it and it's traveling up and it's landing on the substrate, and because the substrate's moved, it's landing on a different area. And we actually get this sort of pulse as it hits. We have like a plume. It's a really bright glow, and so we keep on doing this. We keep on doing this until over long periods of time, until we've built up a film. And yeah, basically in the meantime, we just have these flashes, these constant flashes. So these are some pictures, and we just get these. This is a GIF, so it's actually not that much slower than it'd be in real life, actually, depending on the frequency we're using. But we just get these constant flashes, and then the things move, and then we get another flash, and then it moves, get another flash, and bit by bit we evaporate the material, and we grow a thin film of this material. And so this is kind of interesting. So you could say to me, well, you did in the previous one, you were starting with one material, you evaporate it, you ended up with another one, so why would we change materials? Well, the truth is that these different processes, they provide different energy to the to the flux that we evaporate. It arrives with a different energy depending on the background pressure. Everything is slightly different, so that when it arrives with a different energy, and it will form a different structure. So that's exactly what we're doing. And so with pulse laser deposition, we can tune different things. We can tune the background gas, we can tune the background pressure, we can tune the energy that we give to the laser, we can change the repetition rate, we can change the voltage. There's a whole bunch of different things that we can change, so that when the sputtered flux, the sputtered material arrives, it forms slightly different structures depending on all these different things. And so pulsed laser deposition gives us more parameters that we can use over, say, evaporation, which is you provide the temperature, but that doesn't mean to say that evaporation is a simple process, and there are plenty of things you can tune, but with pulsed laser deposition we've got different properties we can tune. But what's nice about pulsed laser deposition is it's a fairly slow process, so it takes a long time to grow films, but it is quite repeatable. So if we make a film on a Tuesday and then we make one 6 months later with the same conditions, chances are we're going to have basically the same film. It should have very, very similar structure and therefore properties at the end. So yeah, so that's it. That's basically what it is. So that's pulsed laser deposition. That's the technique we use in our lab. We've got 2 chambers. We actually share one laser between the 2. It takes up quite a lot of space. We got kind of a busy lab going on. There's not much space in there. And it's a different way of growing thin film. So as we used before, as we showed in the evaporation experiment, we can also use masks. So some of our students do that, and yeah, so we can grow different films. And yeah, it's fantastic. It was a technique that I hadn't used before coming to Oxford. So when I arrived, we put an order in for a machine. And so we've been getting to grips with it for the last sort of 4 years, 3-4 years that we've had it. And I haven't used it so much myself. It's mostly been the researchers in the lab, but I've got some experiments that I want to do. So yeah, I'm excited to see. So that's pulsed laser deposition, another evaporation, another deposition technique, thin film deposition technique. In the next video, I'm going to talk about magnetron sputtering. So this is my bread and butter. This is what I've been doing for years and years and years. So that might end up being a slightly longer video. Might not. Who knows? You already know some of the basics. So that's cool. And so other than that, thanks very much for watching, and I'll catch you in the next video. Bye bye.